just fine. All right, cool. So tonight, I'm going to do a little stream here, um, looking at this paper called "Advancing Mathematics by Guiding Human Intuition with AI." This is a paper by a whole bunch of people. The one person I know here is Petar Velukovic. I'm not sure if I'm saying that name right. I think it's Velukovic. Um, but he's done a lot of really interesting work, and really like all of his papers. And this paper also kind of showed up on Reddit and was making the rounds. People were interested in it. It was in Nature, the front page of Nature, which is a big deal for if you're in academics. Getting on the front page of Nature is like kind of as good as a paper can do. So, I'm going to try to go through it, see what we can understand. Hopefully, we can get through this whole thing. But I'm excited to check it out. So let's jump into it. The practice of mathematics involves discovering patterns and using these to formulate and prove conjectures, resulting in theorems. Since the 1960s, mathematicians have used computers to assist in the discovery of patterns and formulations of conjectures, most famously in the Birch and Swinnerton-Dreier conjecture, a Millennium Prize problem. Here we provide examples of new fundamental results in pure mathematics that have been discovered with the assistance of machine learning, demonstrating a method by which machine learning can aid mathematicians in discovering new conjectures and theorems. We propose a process of using machine learning to discover potential patterns and relations between mathematical objects, understanding them with attribution techniques, and using these observations to guide intuition and propose conjectures. So this whole thing really interesting because, in a lot of machine learning problems or just like general, places where machine learning doesn't work. One of the reasons is that you can't really, machine learning is kind of a black box. So the idea that this can like propose conjectures sounds neat because I guess ultimately something like that would be really nice whenever you have any kind of like problem, even if it's not in mathematics. Like let's say you have a healthcare problem and you want to like understand, something, why patients are like having some disease, having the ability to get like provable guesses or something out of your model for like why things are happening sounds really interesting. I'm not sure if this is totally going to map onto that correctly, but we'll just see. So we outlined this machine learning guided framework and demonstrated successful application to current research questions in distinct areas of pure mathematics. In each case showing how it can lead to meaningful mathematical contributions on important open problems. A new connection between the algebraic and geometric structure of knots, and a candidate algorithm predicted by the combinatorial invariance conjecture for symmetric groups. Our work may serve as a model for collaboration between the fields of mathematics and AI that can achieve surprising results by leveraging the respective strengths of mathematicians and machine learning. All right, so one of the central drivers of mathematical progress is the discovery of patterns and formulations of useful conjectures, statements that are suspected to be true but have not been proven to hold in all cases. Mathematicians have always used data to help in this process, from the early hand-calculated prime tables used by Gauss and others that led to the prime number theorem, to modern computer-generated data in cases such as the Birch-Swinnerton-Dreier conjecture. Okay. The introduction of computers to generate data and test conjectures afforded mathematicians a new understanding of problems that were previously inaccessible. Sure. But while computational techniques have become consistently useful in other parts of the mathematical process, AI systems have not been able to establish a similar place. Sure. Prior systems for generating conjectures have either contributed genuinely useful Prior systems for generating conjectures have either contributed general use to research conjectures via methods that do not easily generalize to other mathematical areas, or have demonstrated novel general methods for finding conjectures that have not yielded mathematically valuable results. AI in particular, in the field of machine learning, offers a collection of techniques that can effectively detect patterns in data and has increasingly demonstrated utility in scientific disciplines. In mathematics, it has been shown that AI can be used as a valuable tool by finding counterexamples to existing conjectures, accelerating calculations, generating symbolic solutions, and detecting the existence of structures in mathematical objects. In this work, we demonstrate that AI can be used to assist in the discovery of theorems and conjectures at the forefront of mathematical research. This extends work using supervised learning to find patterns by focusing on enabling mathematicians to understand the learned functions and derive useful mathematical insight. We propose a framework for augmenting the standard mathematician's toolkit with powerful pattern recognition and interpolation methods from machine learning, and demonstrate its value and generality by showing how it led us to two fundamental new discoveries, one in topology and other in representation theory. Our contribution shows how mature machine learning methodologies can be adapted and integrated into existing mathematical workflows to achieve novel results. All right, so basically, summarize this stuff. They're just saying, like, you know, we see that numerical methods are really useful, but in math, and if you've studied math, I'm sure you've found that, but haven't really had a whole lot of benefit coming from the AI boom yet. And so these guys are claiming now that they've managed to use some of these new AI methods to help with problems in topology and representation theory. So let's see what they did, and hopefully I can understand the problems, because I'm not much of a topologist or algebra. So guiding mathematical intuition with AI. A mathematician's intuition plays an enormously important role in mathematical discovery. It is only with a combination of both rigorous formalism and good intuition that one can tackle complex math problems. The following framework, illustrated in Figure 1, describes a general method by which mathematicians can use tools from machine learning to guide their intuitions concerning complex mathematical objects, verifying their hypotheses about the existence of relationships and helping them understand those relationships. We propose that this is a natural and empirically productive way. That these well understood techniques and statistics and machine learning can be used in part of mathematicians' work. Okay, so let's look at the flowchart. All right, so they have mathematical steps in gray, computational steps in blue, and they're saying that you hypothesize that there exists an f such that f of x of z is basically y of z. So you generate some data, x of z, y of z, and sample z from some probability distribution. Then you train a supervised model to try to fit this f, find patterns via attribution, interrogate f. Okay, not really sure what that means. So you simultaneously do that and conjecture candidate f. So this just seems like you're saying, like, okay, if you want to see if some function, or so you suppose that there exists some function that's doing something, and then you generate data from which you expect inputs and outputs. Yeah, this is, I don't know, it's kind of generic. I'm not sure why there should always needs to exist some function, but okay, let's just keep going. Let's see. The process helps guide a mathematician's intuition about a hypothesized function f by training a machine learning model to estimate that function over a particular distribution of data, pz. The insights from the accuracy of the learned function f and attribution Sorry, 1 second here. All right, we're back. So where were we? The insights from the accuracy of the learned function f and attribution techniques applied to it can aid in understanding the problem and the construction of a closed form f prime. The process is iterative and interactive rather than a single series of steps. Okay. Concretely, it helps mathematicians. So we just summarizing what we've seen so far in this section. So basically, we're saying that this is all just fluff. But they're saying basically they believe that most mathematical problems, or maybe a lot of mathematical problems, can fall into this kind of framework where you're hypothesizing some function to exist between some inputs and some outputs. And you just train a model that takes you from the inputs to the outputs, and then you interrogate that model, basically. That seems very, very innocuous so far. Pretty, not really a whole lot of room for argument on whether that could work. The problem, I think, is just that actually doing this interrogation is pretty hard and getting anything useful out of it. Okay, so concretely, it helps guide a mathematician's intuition about the relationship between two mathematical objects, x and y, associated with z by identifying a function f caret such that f caret of x is y, and analyzing it to allow mathematicians to understand properties of the relationship. As an illustrative example, let z be complex polyhedra, so that x of z is in z2 cross r2 be the number of vertices and edges of z, as well as the volume and surface area. Okay. So they're just saying x is basically 4 numbers, which is the vertices, the edges, the volume, and the surface area of some shape. And y is the number of faces. Euler's formula states that there is an exact relationship between x and y. In this case, x times minus 1, 1, 0, 0 plus 2 is equals to y, sure. This is Euler's famous formula. In this simple example, among many other ways, the relationships could be rediscovered by the traditional methods of data-driven conjecture generation. However, for x and y in higher dimensional spaces, or of more complex types, such as graphs, and for more complicated nonlinear f caret, this approach is either less useful or entirely unfeasible. Yeah, so they're just saying this thing is like, this is a really simple way that these numbers are related to the number of faces. So they're basically saying, I think this problem is just like not hard enough really to need a method that can generalize to more interesting cases. This framework helps guide the intuition of mathematicians in 2 ways: by verifying the hypothesized existence of structure patterns in mathematical objects through the use of supervised machine learning, and by helping in the understanding of these patterns through use of attribution techniques. In the supervised learning stage, the mathematician proposes a hypothesis that there exists a relationship between x and y by generating a dataset of XY pairs. We use supervised learning to train a function f-caret that predicts y using only x as input. The key contributions of machine learning in this regression picture are a broad set of possible nonlinear functions that can be learned given a sufficient amount of data. If f-caret is more accurate than would be expected by chance, it indicates that there may be such a relationship to explore. If so, attribution techniques can help in understanding of the learned function f-caret sufficiently for the mathematical conjecture candidate f. Okay, so I mean this part so far, I mean this is just very, very simple, really. They're just saying like, and like, you know, I think this is one of those kind of things that a lot of machine learning people do anyway. If you're like trying to figure out whether you can make whether some data like actually predicts some outcome, you can just try to train like a neural net on it, and like if the neural net works, then I guess that thing can predict that other thing. If the neural net doesn't work, then I guess it can't. Okay, so attribution techniques can be used to understand which aspects of f-caret are relevant to the predictions of y. For example, many attribution techniques aim to quantify which component of x the function f-caret is sensitive to. Okay, so yeah, these attribution techniques, I'm definitely not the most knowledgeable about these techniques, but to my understanding, they're not like that good yet. Okay, so attribution techniques we use in our work. Gradient saliency does this by calculating the derivative of the outputs with respect to the inputs. This allows mathematicians to identify and prioritize aspects of the problem that are most likely to be relevant for the relationship. So this is a very, very old trick. Basically, you know, if you have like, if you've studied machine learning at all, you know about gradient descent, and they're just saying you can do like gradient descent of the, you know, not gradient descent. You can find the gradients of the, you know, gradient descent finds the derivatives of the weights with respect to the outputs. The derivative of the outputs with respect to the weights. This is just one thing that people will do to like try to attribute kind of like importance. So for instance, if there's like a classifier for like a cat that like looks at images and like tries to tell you whether the picture is like a picture of a cat, people will like be able to try to find like the cat in the picture by taking like the gradient of the cat output in the model with respect to like the pixels in the image, and pixels that really affect whether something is a cat is like, you know, are assumed to be the cat, right? Because like presumably if there's like a table or something, that's less likely to affect whether that picture is called a picture of a cat or not. So if that's the only technique that they use, I'm really interested to see how they actually get so far with that, with just that. Attribution technique, gradient saliency. I think that's what gradient saliency is. I'm pretty sure that's what they mean, but maybe I'm incorrect. This allows mathematicians to identify and prioritize aspects of the problem that are most likely to be relevant for the relationship. This iterative process might need to be repeated several times before a viable conjecture is settled on. In this process, the mathematician can guide the choice of conjectures to those that not just fit the data, but also seem interesting, plausibly true, and ideally suggestive of a proof strategy. Okay. Conceptually, this framework provides a test bed for intuition, quickly verifying whether an intuition about relationships between those two quantities may be worth pursuing, and if so, guidance as to how they may be related. We have used the above framework to help mathematicians to obtain impactful mathematical results in two cases, discovering and proving one of the first relationships between algebraic and geometric invariance in knot theory, and conjecturing a resolution to the combinatorial invariance conjecture for symmetric groups. Well-known conjecture and representation theory. How about that? In each area, we demonstrate how the framework has successfully helped guide the mathematicians to achieve the result. In each of these cases, the necessary models can be trained within several hours on a machine with a single graphics processing unit. Okay, so I don't really think there was that much new in that last bit. Just basically saying, again, like, I guess they're just saying, you know, you have some inputs, you see if you can train a model that that relates those inputs to the outputs. If you can, you essentially see which of the inputs affect the output the most, using gradient sensitivity, and then from that you can come up with a new conjecture, basically, I guess, saying, like, I guess once you're like realize which variables are the most important, you can kind of say, like, which variables or you can make a new conjecture because you, like, know it must be something that relates to these variables. And they're saying that this process has worked for these two problems, and training these models is relatively easy. One GPU can do it. Okay. Low-dimensional topology is an active and influential area of mathematics. Knots, which are simple closed curves in R3, are one of the key objects that are studied, and some of the subject's main goals are to classify them. To understand their properties and establish connections with other fields, one of the principal ways that this is carried out is through invariants, which are algebraic, geometric, or numerical quantities that are the same for any two equivalent knots. These invariants are derived in many different ways, but we focus on two of the main categories: hyperbolic invariants and algebraic invariants. These two types of invariants are determined from quite different mathematical disciplines, and so it is of considerable interest to establish connections. Okay. Connections between them. Some examples of these invariants for small knots are shown in Figure 2. A notable example of the conjectured connection is the volume conjecture, which proposes that the hyperbolic volume of a knot, a geometric invariant, should be encoded within the asymptotic behavior of its colored Jones polynomials, which are algebraic invariants. And so let's see Figure 2 here. So in Figure 2, hypothesized previously undiscovered relationship between geometric and algebraic invariants, where you have volume, which is a geometric invariant, Chern-Simon something, Myriadonial translation. I don't know what these two things are. Heard of all of them, but not much of a knot theorist. So, but basic idea is that you have some geometric invariants of the knot, things that are the same about the knot, even if you change the. I'm not really sure what transformations you're allowed to do to knots. I think any smushing or rotating or anything like that. Pretty much anything you'd be able to do to the knot in like physical space. And then these algebraic invariants. I'm not really sure what that means. Okay. So our hypothesis was that there exists an undiscovered relationship between hyperbolic and algebraic invariants of a knot. A supervised learning model is able to detect the existence of a pattern between large sets of geometric invariants and the signature sigma k, which is known to encode important information about the knot k, but was not previously known to be related to hyperbolic geometry. The most relevant feature identified by the attribution technique shown in Figure 3a were three invariants of the cusp geometry, with the relationship visualized partly in 3b. The training a second model with xz consisting only of these measurements achieved very similar accuracy, suggesting all right, sorry, I kind of lost my train of thought here. The most relevant features were in 3a, the cusp geometry with the relationship visualized partly in 3b. Okay. So yeah, so they're just talking about doing this process that we talked about here. So they take all these not invariants, um, which I guess doesn't matter that much what they exactly mean, and they did this thing where they trained everything. They found that these three invariants of cusp geometry were the most important ones, and then they trained a second model that only had those invariants, and it got pretty similar accuracy to the first model, so that suggested that that's basically the only important thing. These three invariants were the real and imaginary parts of the meridional translation mu and longitudinal translation lambda. There is a nonlinear multivariate relationship between these quantities and the signature. Having been guided to focus on these invariants, we discovered that this relationship is best understood by means of a new quantity, which is linearly related to the signature. We introduced the natural slope defined to be the real part of lambda over mu, where it has the following geometric interpretation. One can realize the meridian curves as the geodesic gamma on the Euclidean torus. If one fires off a geodesic perpendicular to gamma, it will eventually return and hit gamma at some point. In doing so, it will have traveled a longitude minus some multiple of the meridian. This multiple is the natural slope. It need not be an integer because the endpoint of gamma perp might not be the same as its starting point. Our initial conjecture relating the natural slope and signature was as follows. So they're saying this slope as a geodesic. Okay, so they're just giving one example of a meridian curve where they're saying, suppose you have some geodesic on the torus, and then you shoot a kind of ray off from that. It'll go around the torus and eventually hit the curve again, the geodesic again, but will have gone along, traveled along a longitude minus some multiples of the meridian. I'm not sure what this means. Traveled longitude minus some multiple of the meridian. Okay. Doesn't seem that important to understand the general idea behind the paper, so I'm just going to let that go. Conjecture, there exist constants, C1, C2, such that for every hyperbolic knot k, 2 sigma k minus slope k is less than C1 times the volume of k plus C2. Okay, so they've just set up some relationship here, some conjecture, relating this sigma thing, the slope, and the volume of the knot with these two constants, and they're just assuming that these constants are the same for any knot, presumably in 3 dimensions. While this conjecture was supported by an analysis of several large data sets sampled from different distributions, we were able to construct counterexamples using braids of a specific form. Okay, so they're saying this doesn't work. Subsequently, we were able to establish a relationship between slope k, signature, sigma k, and volume. And one of the next most salient geometric invariants, the injectivity radius of k. Theorem, there exists C such that for any hyperbolic knot k, Subsequently, we were able to establish. Okay, so they're not really explaining how they did that. So they basically say like they conjectured these things because they were the inputs in their original model, and then they found that there was some counterexamples to their conjecture. So I'm not sure why they landed on injectivity to the -3rd. But okay, there exists a constant c such that for any hyperbolic nuclei, blah, blah, blah. Turns out the injectivity radius tends not to get very small, even for knots of large volume. Hence the term injectivity k to the -3 tends not to get very large. However, it would clearly be desirable to have a theorem that avoided the dependence on injectivity of k to the -3rd, and we give such a result that instead relies on short geodesics. Another of the most salient features in the supplementary information, and we give such a result that relies on short geodesics, another of the most salient features in the supplementary information. Further details and a full proof of the theorem above are available in Ref 27. Across the data sets we generate, we can place a lower bound of something on C, and it would be reasonable to conjecture that C is 0.3, which gives a tight relationship. The above theorem is one of the first results that connected algebraic invariance directly implies the signature controls to the non-hyperbolic Dane surgeries on the knot and the natural slope controls genus. Okay, so I'm like, it doesn't seem like they actually proved anything here. Did they say this is just a conjecture? Yeah, they are just talking about conjectures. I see. Okay, I read this a little as being a little more like precise. Okay, well, that's still, I guess, kind of interesting. You know, they came up with some formula relating knot stuff. Okay. All right, representation theory is that, I mean, I also don't understand the knot stuff that well, so maybe I shouldn't be, I'm not trying to like poo-poo it. Representation theory is a theory of linear symmetries. The building blocks of all representations are the irreducible ones, and understanding them is of the most important goal in representation theory. Irreducible representations generalize the fundamental frequencies of Fourier analysis. In several important examples, the structure of irreducible representations are governed by Kasdan-Lutzig polynomials, which have deep connections to combinatorics, algebraic geometry, and singularity theory. KL polynomials are polynomials attached to pairs of elements in symmetric groups, or more generally, pairs of elements in coexter groups. The combinatorial invariance conjecture is a fascinating open conjecture concerning KL polynomials that has stood for 40 years with only partial progress. It states that KL polynomials of two elements in the symmetric group Sn can be calculated from their unlabeled Bruhat interval, a directed graph. One barrier to progress in understanding the relationship between these objects is that the Bruhat interval for non-trivial KL polynomials, those that are not equal to 1, are very large graphs that are difficult to develop intuition about. Some examples of small Bruhat intervals and their KL polynomials are shown in Figure 4. Figure 4. Oh, we never looked at Figure 3. Guys, you never wanted us to look at Figure 3? Okay. So we got some permutations, got some graphs, and somehow it's related to a polynomial. Okay. One barrier to progress in understanding the relationship between these objects is that Bruhat intervals for non-trivial KL polynomials are very large graphs that are difficult to develop intuition about. Some examples of small Bruhat intervals and their KL polynomials are shown in figure 4. We took the conjecture as our initial hypothesis and found that a supervised learning model was able to predict KL polynomial from the Bruhat interval with reasonably high accuracy. So they found that, so what are they trying to connect again? They're trying to connect okay, so there's some conjecture. KL polynomials of 2 elements in the symmetric group can be calculated from their unlabeled Bruhat interval. Boop. Which is a directed graph. So they're saying that symmetric group, I think, is like permutations of list elements. Yeah. Oop, Kendrick Lamar. Oh boy. Yeah, okay. So it's like all the permutations of like a list. So the KL polynomial of 2 elements in a symmetric group can be calculated from their Bruhat interval. Is Bruhat interval going to be like do a quick check? Bruhat interval. Huh. Wikipedia? Okay, doesn't seem like it's that easy. Alright, it's fine. There's some graph you can draw that somehow is related to the symmetric group. And this polynomial, KL polynomial, so these are, I guess, 3 like, yeah, 3 again types of kind of invariance of the, or maybe not invariance, but 3 like pieces of summarizing information about a group. Or not really. It's saying that if you have a pair of permutations, you can make this Bruhat interval or a KL polynomial. And I guess they're saying that they're not sure if these things are necessarily correlated. Or can you like calculate the KL polynomial from the Bruhat graph? Okay. One progress in understanding these relationships between these objects is that Bruhat intervals for non-trivial KL polynomials, those that are not equal to 1, are very large graphs and difficult to develop intuition about. Some examples of small Bruhat intervals shown in figure 4. We took this conjecture as our initial hypothesis and found that a supervised learning model was able to predict the KL polynomial from the Bruhat interval with reasonably high accuracy. By experimenting on the way in which we input the Bruhat interval to the network, it became apparent that some choice of graphs and features were particularly conducive to accurate predictions. In particular, we found that a subgraph inspired by prior work may be sufficient to calculate the KL polynomial, and this was supported by much more accurate estimated function. Okay, that's just kind of neat. So they said, like, they found that, you know, they embed this graph into a neural net, and then they try to predict this KL thing. They saw they could do it. And then they found a subgraph in here that also could do it. So that's pretty cool. Further structural evidence was found by calculating salient subgraphs that attribution technique determined were most relevant in analyzing the edge distribution in these graphs compared to the original graphs. I also like this example a little bit more because, like, they're playing around with how they're representing this graph in their problem, which is like more interesting in my opinion than just like what's the word? Than just like choosing variables. They have like more room for creativity there. Further structural evidence was found by calculating salient subgraphs that attribution techniques determined were the most relevant, and analyzing the edge distribution in these graphs compared to the original graphs. In Figure 5a, we aggregate the relative frequency of the edges in the salient subgraphs by reflections that they represent. It shows that external reflections, those are the form 0i or I n minus 1 for Sn. So swapping the first element or the last element, second to last element, appeared more commonly in the salient subgraphs than one would expect at the expense of simple reflections. Those are the form I plus 1. Which is confirmed over many retrainings of the model in Figure 5b. Okay, so yeah, I guess this graph must somehow be made up of pairwise interchanges. This is notable because the edge labels are not given to the network and are not recoverable from unlabeled Bruhat interval. From the definition of KL polynomials, it is intuitive that the distinction between simple and non-simple reflection is relevant for calculating it. However, it was not initially obvious why extremal reflections would be overrepresented in salient subgraphs. Considering this observation led us to the discovery that there is a natural decomposition of an interval into two parts, a hypercube induced by one set of extremal edges, and a graph isomorphic to an interval in Sn minus 1. So they're saying something like, so I want to see this extremal reflections thing again. It shows that extremal reflections appear more commonly in salient subgraphs than one would expect. Okay. This is notable. So they're saying like the model doesn't have access to knowing okay, how is this is kind of interesting. So they're saying like this graph here, which has these kind of pairwise reflections in it, or pairwise switches in it, gets some like whatever representation embedding or whatever in their neural net, and that representation does not tell you anything about like I guess the order of the or like which nodes represent which reflection, and you can't tell just from the graph, I guess is what they're saying. So the fact that they found that those are important pieces of the subgraph, or that those are important, that those show up a lot in subgraphs that do well at predicting this polynomial, told them that there's something interesting about subgraphs that include these reflections in them. And that was that there's some decomposition into a hypercube induced by one set of extremal edges and a graph isomorphic to an interval Sn minus 1. Let's look at figure 5. An example heat map of the percentage increase in reflections present in salient subgraphs comparing the average across intervals in the data set predicting Q4. So we have the first reflection versus second reflection. Train versus baseline. Oh wait, this one's just a heat trap. B, percentage of observed edges of each type of salient subgraph for 10 retrainings of the model compared to 10 bootstrap samples of the same size from the data set. Percentage of observed edges of each type in the salient subgraph for 10 retrainings of the model. Compared to 10 bootstrap samples. I see. So I guess these are like the gray is like this is just tells you how much more gradient I guess was in the special subgraphs. How much extra gradient. And I guess this is something about the their hypercube decomposition. Sn minus 1. The importance of these two structures illustrated in figure 5c let the proof that KL polynomial can be computed directly from the hypercube and Sn minus 1 through a beautiful formula that is summarized in supplementary information. A further detailed treatment of the mathematical result is given in reference 32. Theorem. Every Bruhat interval admits a canonical hypercube decomposition along its extremal reflections, from which the KL polynomial is directly computable. Remarkably, further tests suggested that all hypercube decompositions correctly determine the KL polynomial. This has been computationally verified for 3 times 10 to the 6 intervals in the symmetric group up to symmetric group 7, or S7. And more than 1.3 times 10 to the 5th non-isomorphic intervals sampled from the symmetric group, S8 and S9. Okay, so for this one, they actually did prove a theorem. But it wasn't quite the computer proving a theorem. It's just the computer giving hints based off of which of these subgraphs were helping find the KL polynomial. But that's actually still pretty cool. I like this one a lot better than the other one. This one's a lot more interesting in my opinion. Conjecture the KL polynomial of unlabeled Bruhat interval can be calculated using previous formula with any hypercube decomposition. The conjectured solution, if proven true, would settle the combinatorial invariance conjecture for symmetric groups. This is promising direction, as not only is the conjecture empirically verified up to quite large examples, but it also has particularly nice form that suggests potential avenues for attacking the conjecture. This case demonstrates how non-trivial insights about behavior from large mathematical objects can be obtained from trained models, such that new structure can be discovered. Conclusion. In this work, we have demonstrated a framework for mathematicians to use machine learning that has led to mathematical insights across 2 distinct disciplines. One of the first connections between algebraic and geometric structure of knots, and the proposed resolution to a long-standing open conjecture in representation theory. Rather than use machine learning directly to generate conjectures, we focus on helping guide the highly tuned intuition of expert mathematicians, yielding results that are both interesting and deep. It is clear that intuition plays a role in elite performance in many human pursuits. For example, it is critical for top Go players, and the success of AlphaGo came in part from its ability to use machine learning to learn elements of play that humans perform intuitively. It is similarly seen as critical for top mathematicians. Ramanujan was dubbed as the Prince of Intuition and has inspired reflections by famous mathematicians on its place in their field. As mathematicians, it is a very different, more cooperative endeavor than Go. As mathematics is a very different, more cooperative endeavor than Go, the role of AI in assisting intuition is far more natural. Here we show that there is indeed fruitful space to assist mathematicians in this aspect of their work. Our case studies demonstrate how foundational connection in a well-studied and mathematically interesting area can go unnoticed, and how the framework allows mathematicians to better understand the behavior of objects that are too large for them to otherwise observe patterns in. There are limitations to where this framework will be useful. It requires the ability to generate large data sets of the representations of objects for patterns to be detectable and examples that are calculable. Further, in some domains, the functions, so just saying, has to be of this kind of special form. So yeah, I mean, ultimately, I guess kind of closing thoughts on this thing. Pretty interesting. Definitely the second example was more interesting. They're really just saying that like you can use this gradient saliency trick to help guide your intuition. Like most of the impressive stuff here really was done by the mathematicians themselves, but it did provide, it seems like it really did provide kind of bits of inspiration for them, and that's really isn't that hard to do. I'm not sure if they show like what their models look like, because like I think if you're like a basic mathematician, like I bet you this like graph model that they used here is probably a little bit interesting. GraphNet architecture, message passing neural net, which isn't that complicated. But yeah. Anyway, pretty interesting paper. I think definitely worth the read, and could be worth looking into some of these results a little bit more if you guys are interested. Anyway, that is, I think, going to be the stream for me tonight. Thanks everybody for watching, and I will see you around. Okay.